Hello, everyone. Thanks a lot for inviting me to this workshop. Today, I'll be presenting a few of the design concepts for energy efficient variable impedance actuators that we have designed in previous years in our research group, which is quite well known for that aspect. So that's kind of an overview of the work that we've been doing recently. I don't want to stress that, we are mostly focused on passive compliance. So we're going to introduce really physical springs, not really dampers, but mostly springs into our designs, rather than actually programming the behavior in control. And there's one main reason why we're interested in doing that. It's mostly because we're, as the title already suggests, interested in energy efficiency. The applications that we actually target, like prosthetics and exoskeletons, especially, they have a strong demand for energy efficient actuators. And this is why we wanted to exploit passive compliance to generate this energy efficiency. Why is passive compliance, or why are springs so interesting? Well, they actually allow for a direct power exchange between the loads and the spring itself, which has energy storage as a main characteristic, of course. And this means that less power is going to be recirculated within the actuator, and as such, there will be less losses accumulated in its components, leading to higher overall efficiency. So that's our general motivation for the passive compliance. Now, a lot of our work on variable impedance actuation started with the MACCEPA principle. In fact, many of the actuators that I will present today are improvements over the basic principle, which I think our group came up with around a bit more than 15 years ago. So the principle is actually very simple. We have a lever arm, which is driven by a servo motor, and this lever arm is connected to the output link through a spring. And so you have the typical compliance behavior, similar to that of a series elastic actuator, in a very compact and energy efficient package. The first proof of concept was designed in 2006. One of the interesting features here is that the stiffness of the behavior can be changed by changing the pretension of the spring, as you can see here. Releasing the spring or decreasing the pretension also decreases the stiffness of the interaction. Now, this was the proof of concept of 2006. So in the past 15 years, we've actually gradually improved this design, making it more compact and more energy efficient, with the aim of implementing it in prosthetics and exoskeletons. You can see a few of the examples here. This is the Mirat exoskeleton designed around 10 years ago, and the Biomod some 5 years ago. Now, the latest generation of MACCEPA actuators is shown on this slide. As you can see, there are some changes to the design. We're now using versus DC motors with spindles to drive the lever arm. And we're also using die springs as opposed to the extension springs that you saw earlier. So those are two major design improvements, in addition to, of course, reductions of the structural mass of the actuator. You can see that we are capable of achieving relatively high peak torques in a relatively small and compact, lightweight package, which is suitable for the applications that we're targeting in wearable robotics. Now, these actuators are also, and I hope the video will play, are also currently being commercialized. So the two previous actuators are actually the core technology behind a new company that we're starting, spin-off company, which is Robotics, where we're trying to sell these actuators as smart actuators, so with integrated electronics, and bringing them to the market as a modular solution for exoskeletons, cobots, and other devices which can make use of compliant actuation. So if you're interested, certainly go to the website and get in touch with our researcher entrepreneur Victor Grosu. Besides the compliance, we're also looking at integrating locking mechanisms into our actuators. And so we have a review paper that was published a few years ago, 2015, in IEEE Robotics and Automation magazine, where we discuss the different locking mechanisms that could potentially be used in robotics. And we also present methodology for their selection. There's a nice flow chart in the paper as well. Locking mechanisms are actually the basic, one of the important components of one of our flagship, let's say, devices, the Amfoot ankle prosthesis, where it actually helps to, first of all, adapt to different slopes. And it also helps with flattening the torque requirements for the motor, as you can see here. So actually with this prosthesis, we're able to deliver a constant torque with the motor, which is interesting from an energy efficiency perspective. And at the output, we can deliver a curve, a torque curve, or a power curve in this case, sorry, which is similar to that of the human ankle. So that's also a successful implementation. Also here, we're trying to bring this solution to the market. Startup here is called Axiles Bionics. This is one of the earlier prototypes. I think it's the 4th iteration of the Amfoot. And currently the company has grown considerably, already 18 employees. And we do hope to bring the first true prosthesis to the market very soon. Next, I'd like to talk to you about another concept, which we call redundant actuation, and which essentially consists of joining or using multiple motors to drive a single output. And I'm going to talk about a few of these concepts today. It was also part of my PhD research. So one of the devices that we built was what we call the dual motor actuator. I wasn't very inspired when I chose the name. It basically consists of 2 motors coupled to an output load through a planetary differential. Now, this system is statically determinate, meaning that if we define a static output load, that the static input torques from the 2 motors are completely determined. But it is kinematically redundant, meaning that any output speeds can be generated with various combinations of input speeds from the 2 motors. And the relationship is given by this equation, in which the gear design of the planetary differential plays a prominent role. We've actually shown that this actuator can improve the energy efficiency of a specific load profile or a specific robotic application by distributing the energy requirements or the work requirements over the 2 motors in a smart way. So because of the kinematic redundancy, we have some room for optimization there. We showed in this paper that actually the decrease in energy consumption is most pronounced at relatively high speeds and at low torques. This is also where brushless DC motors usually perform the worst. The approach, of course, doesn't include a spring, as I presented in the previous schematic. We can combine the dual motor actuator with a series spring, which results in a series elastic dual motor actuator. And as such, we can benefit from the benefits of kinematic redundancy and compliance at the same time, with an energy reduction of 16% compared to an optimized series elastic actuator design for an ankle prosthesis. So this is also a promising result. We also took this idea a step further. So the idea of combining motors with springs, and I didn't really talk about them, but there are also locking mechanisms integrated into the dual motor actuator. And so combining multiple of these units of motors, locking mechanisms, and spring results in a design which we call the Plus SPA. And you can really see it as a set of parallelistic actuators mounted on the same output shafts, of which the equilibrium position of the spring, of the parallel spring, can be adjusted through the motor. So this can also allow you to statically compensate for gravitational loads. This plus SPA concept, we also made a modular version of it, as you can see here, which allows you to stack different SPA modules onto each other to augment the output torque created by the actuator. And as a proof of concept, we also designed a robot arm with this actuation principle. So this is an impression of what it would look like. And then finally, because the time is up, we also improved this concept somewhat. Because of course the weakness is that we're using 4 motors to drive the output, but we could actually reduce that to one single motor combined with a smart intermittent mechanism. You can see the mechanism here. So one rotation of the motor is designed in such a way that it can actually recruit different springs depending on the motor position. You can see the mechanism in action here, mechanisms to the left, and you can see different springs being recruited. It's also important to note that there's always one spring between the motor and the output, meaning that we have true passive compliance behavior in the ISPA. All right, and those are just some of the concepts that we've been working on in our research group in recent years. I'd be happy to take any questions if there are any left. And otherwise, you can also connect to me on social media or by email, and I'll be happy to answer more questions there.